Okay, so I'm going to make things a little easier for you. We're going to come up with some general rules for antiderivatives, so you don't have to think so hard when you play Calculus Jeopardy, right? So let's start with, I want to demonstrate here how every one of our derivative rules can be converted into an antiderivative rule. So let's take, for example, this one. Let's take the derivative with respect to x of sine x. What's that equal to?
Negative cosine.
Yeah.
No.
No, it's cosine.
Cosine.
JB.
Okay, so here's the recipe for calculating the corresponding antiderivative rule. All we got to do is we're going to, first of all, we're going to write this in differential form. Okay, so this in differential form, this would look like the derivative of sine x equals cosine x dx, right? Everybody agree? Okay, and then I'm just going to anti-differentiate both sides, and the word we'd use is integrate both sides, right? And what's that do? So the antiderivative of a derivative does what?
It just makes it sine x.
It just cancels it, right? To within a constant, right? And then over here, well, there's our rule, right? So if we flip this around then, we're just going to get the antiderivative of cosine x dx equals sine x plus c. How about that, right? So we could probably do this quicker. We know that if the derivative is cosine x, then that's the answer to the antiderivative, right? So we could take all of our derivative rules and just flip them around. So for example, you guys tell me then, what's going to be, if we take this one, the derivative with respect to x of secant x equals what? Okay? And so then what's the antiderivative rule going to be? The antiderivative of, yeah.
Oh, yeah.
Plus c. Plus c.
Yeah. Right? You get it? See how those are all going to work? So each one of those we can flip around. The one that's probably the hardest to see, let's go through this one together. This is kind of a cool one. What if we did the power rule? So I'm going to use k's in the derivative one. You'll see why. So the derivative with respect to x of, do they give these to you with u's, or we're just doing x's for now? That's fine. Yeah. Okay, that's fine. So of x to the k is what?
Kx, k minus 1.
Okay, to the
K minus 1.
k minus 1. Okay, good. So then, how could we flip that around, right? So if we flip that around, yeah, we're gonna get the antiderivative of k x to the k minus 1 dx equals x to the k plus, call it c1. But that's pretty hokey, right? That's pretty hokey to write it that way because that's really contrived. What are the odds that we're going to have just the right value of k stuck inside that derivative rule? None. What we want to have instead is we would rather just have a derivative rule that looks like this. I mean an integral rule that looks like this. We'd rather have one that says the integral of x to the n dx, or the antiderivative, equals what? Right, so we got to convert this a little bit. That's easy to do. Let's just make a little substitution. if I want to make this rule look like the more compact and useful purple rule, what should I probably, how do I relate the n's and the k's?
N equals K.
N equals k, that would just give me n minus 1
no,
here.
we're backwards, okay, never mind.
So n could equal k minus 1. Everybody see that? So if we let n equal k minus 1, that's helpful, right? Because then I get an n right there, but then what do I get with this constant? That constant would be n plus 1, wouldn't it? Why don't we put the constant out front though, right? Because we can do that. We haven't really learned that yet, but we can, because think of the inverse nature of an antiderivative. With derivatives, we can always, when we're taking a derivative of something, we can always put the constant out front, right? So, and that constant's going to appear in the answer, right? Just distributed through. Make sense? So I'm just going to do a little hand waving here then. Does it make sense to you that, that's what we call this in physics, is a little hand waving. I'm not going to give you a formal definition or formal proof, but this will make sense. Shouldn't it make sense then if I reverse the process that constant is still separate from the process, right? So I should be able to pull the constant out front of an integral also, or an antiderivative, we'll call it for now, right? So let's take this k and let's move it outside, and the k is going to become an n plus 1, right? Well, what do we get over here? For our answer, we get x to the k, which is n plus 1 plus, call it c1, right? Oh, what do we got, right here?
A note.
Okay, thanks.
Well, not
Not here.
chance.
Oh, yeah, not here.
I think it's one out of 5 chance. Here, no, here.
He's got a key.
Okay, so then this is what we get, but this is really inconvenient still. It's really contrived. We're not going to have that n plus 1 out front, right? So let's divide both sides by that. Okay? So if I divide both sides through by n plus 1, then those cancel, and this is much better then. Right now I end up with, on this side, I've just got the antiderivative of x to the n dx equals. Well, let's split this fraction, right? Let's split it into two separate fractions. So I get x to the n plus 1 over n plus 1. And what's that going to be? What's c sub 1 divided by n plus 1?
C.
C. Just call it c. So there's my rule. Okay. Doesn't that's a much better rule, isn't it? Right? Much better rule. Okay, so there's our general power rule for antiderivatives. Okay, so now let's put these things into use. I gave everybody a handout with a list, I'll put it on Moodle too, of all the results of doing this, right? Okay, so let's try a couple problems. What are my notes here? Lecture notes. Am I gonna have to wing it, which is okay, but... Oh, here we go. Okay, so let's try...
Oh my God. I'm honestly about to die.
Dude, I'm losing my touch. I can't eat as much as I used to.
I should have quit after 2, but here we are on number 3.
Oh, yeah, I did 3.
And second best I have to do some like multiple chia stuff. It's fine, whatever. Who needs to live?
We did this one the other day, right?
Oh,
I think we
I
did.
think so.
But let's think about this using our rules now, right? This one happened to work out great to just play calculus Jeopardy. But let's think about this in terms of some rules. How can we simplify this antiderivative? Well, first of all, what did we say we could do when we have multiple terms in our integrand? Split it. We could just split it up, right? So we'll break this up into the antiderivative of x to the 1/2 dx plus, okay, now what? Now what about this guy? How am I going to rewrite this one? Antiderivative of 1 over the square root of x is x to what power? Negative 1/2. And what about that what about this 1 over 2? Well, that's a constant, right? So I can pull that out front. Okay?
Should be negative.
And now this fits. And here's the thing you gotta understand about antiderivatives. They're harder. Antiderivatives have to fit one of our general rules, or we don't have anything to do with them, right? We don't know what to do. We've got a fairly limited list of general rules right now, but as we go throughout the year, we'll add some more. And when you go to college, you'll even add some more. Like, we won't add the hyperbolic trig functions, for example, okay? But you'll get those in college. Eventually, when you're doing like really hard integrals, antiderivatives, I remember in college, something that you routinely do is you'd look in a book that has a table of standard integral forms, where you just search for ones that match the form that you've got in the integrand.
Gross.
Yeah, a little bit. More and more now, that's done for us symbolically, right? I mean, that's something that computer algebra systems will do, is they'll symbolically integrate functions, right? Which is pretty cool, which allows us to get a little bit lazy, but you still have to be good at the calculus, because being good at the calculus allows you to expand this thinking to other processes that require you to be good at calculus, right? But at some point, it's just a matter of matching patterns, and you might as well let a computer do it for you, right? So, so what's the answer to this one then by our power rule? What's our power rule, right? Let's go back and have a look, right? Here's our power rule. You've got it on your sheet. The antiderivative of x to the n dx is going to be x to the n plus 1 over n plus 1, right? Okay, so if we apply that, what's that going to give us here?
I think it would often use the physics.
So that's going to be x to the, what's n plus 1?
And plus
N's 1/2, right?
Oh, yeah, it's just 3 halves.
3 halves, okay, so we get x to the 3 halves divided by 3 halves. Well, we never divide by fraction. What do we do?
multiplied by 2/3.
Multiply by the reciprocal. So we get 2/3 x to the 3 halves plus n is negative 1/2. What's n plus 1? 1/2.
Oh, it's like the constant.
So we get x to the 1/2, and then we've got our 1/2 out front. So, but we're not done here, right? That's n plus 1, but we have to do x to the n plus 1 divided by n plus 1. Well, what's the reciprocal of 1/2? 2. So then, that's our answer, and those cancel, right? See how that works? Okay. All right, let's try another one. This just takes a little practice, and what I want you to kind of focus on now, we're going to look at some examples where we have to rewrite the integrand. Okay.
How many do you have?
I had 3.
Okay, so we all have.
You guys are looking like you are hurting a little bit here.
So.
So-
Those not great choices.
Yeah.
I like it.
Well, you learn from those kinds of choices.
Yeah, I learned I should try perform next time.
Yeah, try for 4. You eat them faster, then it doesn't hit you as fast, so you
True.
can eat more.
True, that is true.
Okay, I'm gonna have to rewrite that integrand, right? Because if I look at that integrand right there, that's weird. That does not match any of our standard forms. But I can easily rewrite that. What's that gonna become?
2.
Integral of
X squared over x squared is 1.
1.
Plus
1 plus,
It's 1 over x.
so that's gonna be x to the
-2.
negative 2, right? And I'm not gonna, and here's the other thing too, like we did before. You guys are smart. Take some shortcuts. I have some kind of pie in my hands there. So, x to the -2, we're not gonna explicitly write that as separate integrals. We'll just anti-differentiate term by term, right? So then this is gonna give us what?
What happened to the original x squared?
I split it up. Split the denominator.
X squared over x squared is, it's like 2 over 2.
That's like river divided by river.
Okay,
So
well,
that's an
where's
indeterminate
Where's
form
the x
right
to the
there.
negative 2 over? Wait,
So what's the antiderivative of 1?
Nothing.
No, derivative of what is 1?
Oh, 1 x just
Oh.
x.
X, right? Okay, technically, you could actually apply the power rule there, couldn't you? Because 1 is x to the 0. So n is 0, what's n plus 1?
1.
Ah, how about that? It's kind of a goofy thing to do, but you could, right? You get x to the 1 over 1, right? So we get x, and what's this guy going to give us here?
A number?
Let's see, so it's gonna be -1.
Okay,
So then,
I'll write it that way.
okay,
Divided by
2.
-1
1.
makes it a minus. And we're done. Right? Make sense? Okay? Okay?
I'm still confused on where the x squared over.
Yeah,
x
I really don't
hang on.
understand the x.
Because x squared over x squared equals 1 to me.
Right, but what's 1 over x squared?
Oh, wait, okay, I see how you.
So,
You can
here.
solve it like that?
Oh.
I didn't know you could split it like that, I guess.
Oh yeah, it's just common denominator.
Okay, that
right,
makes sense,
yeah.
that makes sense.
Okay.
And you have to do it that way.
What an linearization.
Yeah.
Or what an integral.
Yeah, that's
What
right.
an anti-derivation. Derivation.
I mean, you almost have some options there, because you can say, what integrations? That's not so severe, but if something's really crazy, what an anti-differentiation is going, I mean, that gives you some
That's a
options.
mouthful.
Yeah.
What irradiation?
That's like when your parents use your middle name, you know, there's a problem. Okay, so let's try,
Can we like offer these pies to people in physics, because I don't wanna take these.
yeah, I'm sure we can. I think they probably would accommodate you.
I'll just take my
Okay, so how about, let's see,
I know.
okay,
It's like 4 pieces.
I'm just gonna do this.
I might steal just like a small sliver of that.
I'm not, because
Sliver.
if I
Well,
do, then I'm gonna eat it.
Unless you want me to
Oh,
take
yeah.
more. Yeah.
I already have diabetes, and I don't need more diabetes.
you go for Kremlin?
So is
Okay,
that.
like,
You do?
Oh, no.
Perfect.
I brought 10.
Awesome.
Okay,
I
just
don't know how physics.
a slice
that
or
they're not gonna
slice
like
by
a
slice?
little
Physics isn't.
I don't know, whatever Stephen uses. Whatever you want to use. That is easiest.
Yes. Okay, what about that? What are we gonna do with that?
Okay.
Like, I'm not even.
Chain rule.
So you can't, there is no chain rule for anti-differentiation. It's much more complicated than that.
Thank God.
It's much more complicated, Braden.
There is something that will eventually get
So,
you.
should we be able to solve this right now?
No, you can't,
No.
because
Okay.
there is no standard form that looks like that.
No, as in like us with our knowledge.
Yeah,
Yes.
yeah, you should. But what do you have to do?
Can you distribute the exponent?
You can't distribute the exponent, because you
No,
can't
no,
distribute an exponent over a sum, right?
Perfect.
Okay, yeah.
So you'd have to just expand it out, right?
So
So
can
using
just write it as
Pascal's
3t
triangle,
squared
yeah,
minus
what's that
2
gonna be,
times
right, so-
3t squared minus 2.
So if I take something like a plus b squared, that's just a squared plus 2ab plus b squared, right?
Okay.
So
Yep.
what's this gonna become? What's the integrand gonna become?
3t to the fifth.
9
T to
t
the fifth.
to the
6.
6,
Oh, it's
right? Because you're squaring it, right?
Yeah.
Plus 2 times a times b, so that's gonna be minus
6.
12.
Oh, hey, I was doing minus 6t cubed, minus 6t cubed.
You see what I'm saying? It's
That's
minus 2ab. 2 times a times b,
Oh, yeah.
negative 12 t cubed.
Plus 4.
Okay.
Woo!
No, yeah.
When you can do math.
Okay, and that's trivial from there. We don't even,
Yeah.
right? I mean, then we just have power rules stuff,
Yeah.
right?
Power.
Okay.
Easy.
We'll just do one term. What if we just do the first term?
Oh,
So the
we did
first
last-
term-
Last term, every.
First term is gonna be 9, we leave the 9 out front. What's the antiderivative of t to the 6th?
6.
6. Oh, wait.
7. So t to the
T
7.
to the
7.
7.
divided by
6.
7, that's a
6,
t.
7.
So 9/7 t to the 7th,
Yep.
right? Plus, we can just do this real quick. Minus, what's this one gonna be? T to the 4th over 4. 12 over 4 is
3.
3, so we get a minus 3 t to the 4th plus
4x.
4t plus c. Done.
40.
40. Yes.
Okay?
40 makes the numbers go round. Or is it
I have
42?
no idea what I'm gonna do for lunch now, but I'm not going anywhere.
Yeah, I think we're. I think we're in pretty good shape. You guys could do,
Can you stay there? Don't mess my stuff up. Can we do that?
you guys could do
It'd be sick, actually.
those. You could do the trig one, same idea. Okay, but now let's move on. Now let's try something like this. Let's solve, I want two things from this. I want the general solutions and general solution of this differential equation and the particular solution. So here's the differential equation. Okay, here's going to be the particular condition.
Has to fit with.
In other words,
So
this
that
is
is
saying,
the derivative, we need to anti it, or?
yeah, right. So this is a differential equation is just an equation involving one or more derivatives, right? So this is what we call a simple ordinary differential equation for reasons I'll explain to you later. But all we have to do is undo this thing, right? Whatever the derivative is equal to becomes the integrand of the antiderivative, right? If you're unsure, here's the process. Remember we went through this the other day. I think you were gone. There's a way we can always algebraically convert a derivative, a differential equation, into an integral. So I'll put it in standard form, which means I multiply each side by dx, right? And this will make sense. This is real simple. So then we end up with dy equals the quantity 2x minus 1 dx, and then what do we do?
Just.
Right.
Integrate it,
And so we end up with y equals
X squared.
the
minus X.
antiderivative of that, right? Okay, and we'll just hold the constant until after we've done the process, right? Technically, you're gonna get a little constant from each side, but we'll combine them into one. We never do that work. We just always slap a big plus c at the end. Okay, so what's the general solution of this differential equation?
X squared, minus X.
Okay,
plus C.
good. So y equals x squared minus x plus c. Very good. Okay, so what happens if I change the values of c? If we look at a couple trajectories of this general solution, what the general solution always represents is an infinite family of curves. Okay? And that's all it really is, isn't it? Right? So, I mean, do I even need to show you that? It's just going to be parabolas that are going to be lifted up, right? Okay, so that's the general solution right there, because it's got a plus c in it. It represents a family of curves. Now we want the particular solution, though. So if we want the particular solution corresponding to this condition, that's going to specify exactly one trajectory out of that family, isn't it? It's going to pick the one trajectory, the one parabola that goes through the point x equals 1, y equals 1, right?
We just plug one into.
You just plug them in to find c, don't you? Right? So we'd end up then with 1 equals 1 minus 1, which is 0, plus c.
So X equals 0.
So c equals 1, right? So then that just tells us that the particular solution is y equals x squared minus x plus 1. Okay? Now this is just the first inkling of what you can do with this, but differential equations are huge in physics. Because think what differential equations do. I'm just going to talk conceptually for a second here. Think what derivatives do compared to static equations. Static equations are boring. Static equations could be used to represent maybe some forces or some geometry or something, but it's not changing. What if we want to model, for example, the vibration of a guitar string? If we want to model the vibration of a guitar string, then we've got to look at things like each one of the particles on the guitar string. We've got to look not only at what its position might be, but also what its velocity might be, right? So think about a guitar string then. If we've got a guitar string, and let's say we're looking sideways at the guitar, so this is the fretboard, and there's the nut, and there's the end of the, this it is where you press your finger on a fret, let's say, right? So then what's going to be, if I look at these points right here, what's going to be the amplitude of the vibration at the nut on the end of the guitar and at the fret where you're depressing the string?
That's what we find out.
0, right?
0.
See, because those are the places in between. The string could do lots of things. It could vibrate like that, or it could vibrate like that, or it could vibrate in all these harmonics, right? But if we want to set up a differential equation then, we could set up a differential equation and we could impose these conditions on the differential equation. And we could come up with, does that make sense? So we could come up with some particular solutions of what are going to be the vibrational modes of this string based on the initial conditions that we set up. I mean, there's a lot behind that, but you get an idea where you could go with this, right? Okay, I mean, isn't that cool that you can do stuff like that and you can mathematically come up then with and make predictions about what the frequency is going to be, you know, what the pitch is going to be, what are the pitch of the harmonics going to be. You know, it's just one way you could approach it is with calculus. Okay. So let's try another one. It's getting too easy. Let's try a little harder one.
You're saying this with a not stuffed stomach. I'm about to blow.
Yeah.
Related rates, how you can use
Okay, let's try this one.
As you get older.
How much time we got?
4
4
minutes.
minutes.
Gosh, that's not enough.
We need a block period. don't
We do. We need like 3 hours a day. Seriously.
I mean, we could just.
Well, we could do with 3 hours a day.
I mean,
As
we
long as you
could,
had,
but
like,
I
a
don't know
break
if we
after an
need
hour and a
3 hours.
As long as like for like 10 minutes in the middle, we have like a little.
Maybe if we had a lot more just videos for fun, I could deal with that. You know?
I mean, I'm not sure if I can really get up and leave for lunch at this point anyway, so
Yeah.
I'd still be here.
Might as well just stay till physics.
I don't know about that far.
Yeah.
Let me eat lunch.
You say you'd.
Okay, what about this one? Oh, this is so cool. So what do we do here? So we've got a second derivative, right?
Yes.
So how do we undo a second derivative?
We do
Do
the
it twice.
antiderivative.
Okay,
Twice.
right. The second derivative is the derivative of the first derivative, right? So does this make sense then? Does it make sense that we could say f prime of x is equal to the antiderivative of f double prime of x?
Yeah.
Right?
So is that essentially an antiderivative of derivative of derivative?
Yes. Yeah, that's the symbol, right? Remember, this is what we call the integration symbol, and that's the variable of integration. And really, the part that we focus on is the integrand, which is in between. Okay? So what's the answer to that?
2x.
2x
Plus it.
plus, we'll call it c1. Okay? Okay, good. So now let's go further. So now, if we want to find the function, f prime is the derivative of the function, right? So f of x should equal the antiderivative of f prime of x, right?
Yes.
Which is that. Aha. So we get the antiderivative of 2x plus c1 dx. Okay, so what's that going to equal?
X squared plus c2
Plus c1
plus c2
Let's see.
plus c2.
antiderivative of c1,
Oh, plus c1x.
c1x
Whoa, that's spicy.
plus c2. Aha. So now let's go back and let's plug in our initial conditions. Okay, so one thing we know is that f prime of 2 equals 5, right? So we could go up to the orange equation right here. Rather than deal with these both at once, we could go up to the orange equation and say, okay, well then that means that if I evaluate this at 2, right, shouldn't this give me 2 times 2 plus c1 equals 5,
Yeah,
right?
so
So what's c1?
One.
1. Okay, so c sub 1 equals 1, and so we could come down here and change that to a 1, and now we can use our other
C2 is 4.
particular condition and figure out what c2 is. Exactly, so we could say when we evaluate c2 or we evaluate f at 2, we're going to get 2 squared plus 2 plus c2 equals 10. Right? So then what do we get? C sub 2 equals 4. There we go.
That's nifty.
Isn't that cool?
That is
And so then we end up with the particular solution, f of x equals x squared plus x plus 4. That's really cool. Think what we did there. We found the one function whose derivative passes through this point and for which the function passes through that point.
That's nifty.
How many pieces of particular information did we need? How many particular conditions did we need?
I think I
We
had
needed
two.
two, because we had two unknowns to account for, right?
He's talking about
Would those,
pieces,
now,
right?
here, last question. Did one of those need to be a derivative? No, it didn't. We could have been given two pieces of information about the function, for example, right?
Yeah.
It just would have been a little harder problem, but we could have done it. You guys you wanna just put those in here
Sure.
till physics?
Yeah.
Hi guys.
What's that?
Can I just take my time?
Oh, that's fine, you can, that's fine.
I just don't want to.
If you, I mean, you don't have to, if you wanna just like leave them here for physics.
I'm just thinking
Let's put them, put it right in here then, how about, this will be safe. So like,
what do you do?
I don't wanna end up like you guys, I'm just saying no to overindulgence. Bye.
What do you do for lunch? Just sit here and watch calculus videos?
What's that?
Do you just sit here and watch calculus videos for a while?
I just kinda, I mean, usually I gotta just work, but every once in a while I'll watch it. I'll go through some cool math stuff. Keep the momentum going.
Are you like a huge audiophile?